Hi everyone, let us discuss Stokes theorem. First we will discuss its statement and then we will discuss its proof. Okay. So what have they given? We have a vector valued function f bar. So we have a f bar here which is continuously differentiable and it is a vector valued function. So here we consider f is from R3 to R3, right? So we have a smooth surface here. You can consider any surface. I am showing it here, this one. So this is a surface in R3 having a curve boundary C. Okay, so here we denote the boundary of that surface by C. So this theorem says the value of line integral of f bar over C is same as value of surface integral of curl of f bar over that surface S. So this thing we have to prove. Okay, so let us start to discuss its proof. Okay, so let me write here proof. So here we have a vector valued function capital F bar. So it's a vector valued. So that's why I will consider it as f1i plus f2j plus f3k. So let me write here, let f bar is equal to f1i plus f2j plus f3k, right? And here we consider a position vector r bar, and r bar is equal to, it is obviously xi plus yj plus zk. So it's a position vector. Then obviously dr bar is equal to dxi plus dyj plus dzk, right? So what we have to prove? We have to prove that value of this line integral is equal to value of this surface integral. So we have to simply prove that these two integrals are equal. Okay. So let me write here what we have to prove exactly. So to prove that, TPT, to prove that integration over C f bar dot dr bar is equal to double integration over S curl of f bar dot n cap ds. Okay. So let me put the values here. We will simplify it and we will find what we have to prove exactly. Okay. So that is to prove that integration over C f bar means f1i plus f2j plus f3k dot dr bar means this one, let me put here, dxi plus dyj plus dzk, right? Let me write it here, is equal to. So let us simplify this right hand side also, double integration over S. So curl of f bar, you know that curl of f bar means del cross. Curl means del cross and divergence means del dot. So curl of f bar means del cross f bar, but f bar is nothing but f1i plus f2j plus f3k dot n cap ds. Obviously we have to take the cross product first and then dot product with n cap, right? So finally we have to prove this line integral is equal to that surface integral. So let us simplify it more. That is to prove that. Okay, I will simplify it more. So there is a dot product, you know well how to take a dot product. Multiple of I into multiple of I plus multiple of j into multiple of j plus multiple of k into multiple of k. So that is to prove that integration over C f1 dx, right? f1 dx plus f2 dy plus f3 dz. So this is equal to, so here also I can split in the same way, double integration over S. So del cross f1i plus del cross f2j plus del cross f3k dot n cap ds. Since still we haven't started its actual proof, we are simply working on what we have to prove exactly, right? So here as you know, if addition is there, subtraction is there, we take a separate integration. So I will do the same thing. So therefore, or that is to prove that integration over C f1 dx plus integration over C f2 dy plus integration over C f3 dz is equal to, I can do the same thing for this surface integral also. So double integration over S del cross f1i dot n cap ds plus double integration over S del cross f2j dot n cap ds plus double integration over S del cross f3k dot n cap ds. That means we have to prove exactly. Simply we have to prove that the sum of these three line integral is equal to sum of these three surface integral. Now it is enough to prove the first line integral is equal to first surface integral, second line integral is equal to second surface integral, and the third line integral is equal to third surface integral. Okay. So what will we do? We will simply focus on first line integral and first surface integral, and we can write similarly, we can talk about the remaining two line and surface integrals. Okay. So let us focus on that, this line integral and this first surface integral. Okay. So there is no more space to write, make a screenshot of it, then I will go further. So now I am starting to work on first surface integral. Okay. So that is there is del cross f1i. So there is one term in the first surface integral, del cross f1i. Let us start to work on it. So you know that del means I del by x plus j del by y plus k del by z. Cross f1i, that means actually f1i plus 0j plus 0k. So we have to find cross product of these two vectors. So you know well how to find a value of cross product by solving a determinant. Okay, having a first row I, j, k, second row is obviously multiples of I, j, k here, and the third row will be the multiples of I, j, k in the second vector, that is f1, 0, 0. So you know well how to find a value of determinant. I, product of these two 0, minus product of these two 0, minus j, always middle term we write a minus sign, product of these two 0, minus product of these two, that means dabba f1 by dabba z, plus k, product of these two 0, a minus product of these two, that means minus dabba f1 by dabba y. So let me write properly what we have here, minus minus plus dabba f1 by dabba z, j, right, minus dabba f1 by dabba y, k. So this is value of del cross f1i. So this is a very important thing for us, we are going to use it later. So let me call it as equation number 1. Okay, so this is equation number 1 and this is very important thing for us. Okay, so let us focus on diagram now. Okay, we have some space, let us write. Okay, so here what we have a three-dimensional figure, z-axis, y-axis, and this is x-axis, x, y, z. So we have some surface S here having a boundary C. Okay, I am showing here. So we have a surface like this S. So this is our surface S having boundary C. So this is the boundary C. So what we do, we take one point P on that surface S. Let P be any point on S. So let me show in a diagram. So this is point P. You can easily see there is one point P on surface S. So I consider a small element, okay, of S which encloses point P. So let ds be an element of S encloses point P. So let me show in the diagram so you can easily understand. So this is a small element ds. I hope it is visible to you. So this is ds, that means it is a part of S which encloses point P. So now what we do, we take the projection of that surface S on xy plane. So I am taking its projection on xy plane. Okay, I am taking its projection of this surface S on xy plane. So we have a diagram like this. Okay, we have a diagram like this and I am denoting it by R. So let me mention here, let R be a projection of S on xy plane. Okay, on xy plane. And obviously we have a small element ds, so its projection will be somewhere here. I am denoting it by dx dy. Okay, so that is dx dy. So that surface S has also some equation, so I am calling it as z is equal to f of xy. So let z is equal to f of xy be an equation of S. So obviously f is continuously differentiable. Clearly f is continuously differentiable function. Okay, so now everything I have written here, right? Everything I have written. So let us repeat what we have. We have a surface S, right? We have a surface S. So let me show like this. So this type of surface we have. So there is one point P. There is one point P on that surface S, getting? And we have some small element ds which encloses that point P. So we have a normal vector also. So let me show it here. So let n cap be a normal vector. Okay, as you can see here, this is a n cap, unit normal vector, okay, to at point P. So let n cap be an unit normal vector at point P. So we have a unit normal vector R be a projection of that surface S on xy plane, right? So obviously we have a dx dy which will be the projection of that element ds. This thing we have, as well as that equation of that surface S is equal to f of xy. So obviously f is continuously differentiable. So then we can express ds in terms of dx and dy. So ds is equal to dx dy divided by, so you know that, so we consider a normal vector n cap, so I should write n cap here, and we are taking projection on xy plane. So we want a normal vector, okay, with perpendicular vector to xy plane. What is a unit normal vector perpendicular to xy plane? That is obviously k, which is in a direction of z axis. So you know that we have a vector k, we have a vector I, and we have a vector z here. So the vector perpendicular to xy plane, that is k, so I should take a dot product with k. You can write k cap, or simply you can write k also. So therefore dx dy is equal to, I am taking this n cap dot k on this side, so n cap dot k, or you can write k cap ds. So this is the second important thing we have got. So let me call it as equation number 2. So here we have equation number 1, we have equation number 2. All these things we are going to use later. Okay, so make a screenshot of it, then I will go further. So let us find vector equation of surface S. Okay, so you know that vector equation we always write in this way: xi plus yj plus zk, right? So zk. So here you can write cap, or you can write as it is izk, or you can write I cap, j cap, or k cap, right? But what is the equation of that surface? Is z is equal to f of xy. So let us put the value of z here. So we will have xi plus yj plus f of xy k. So now what will I do? I am going to differentiate with respect to y. So let us find its derivative with respect to y. So deba r bar by deba y is equal to derivative of x with respect to y 0, obviously, derivative of y with respect to y 1, so that's why I am writing simply j, and derivative of f with respect to y deba by deba y k. So this is value of deba r bar by deba y, but it's a tangent vector. Okay, so here deba r bar by deba y is a tangent vector. Okay, so it's a tangent vector. So you know that n cap is a unit normal vector. So let me show here. So suppose this type of surface we have. So we have a tangent vector like this, and n cap is a normal vector. So yes, what is the angle between them? So obviously the angle is 90 degree, getting? So these two vectors are perpendicular to each other. So that's why their dot product will be 0. So tangent vector, and n cap is a normal vector. So it's a normal vector, getting? So it's a tangent vector, it's a normal vector. So that's why their dot product will be 0. So therefore deba r bar by deba y dot n cap is equal to 0. But see the value of deba r bar by deba y we have got here. So let me put this value here. So let me put the value of deba r bar by deba y here. So j plus deba f by deba y and dot n cap is equal to 0. So you can take a dot product. Okay, let me write here, and let me remove this diagram also. Okay, so let us take a dot product. That means you will have j dot n cap plus deba f by deba y k dot n cap is equal to 0, right? So we can shift this term on that side. So we'll have j cap dot n cap is equal to, you can write cap or no need to write cap, having a same meaning, del by del by y k cap dot n cap. So this is the third important thing we have got. So this is my equation number 3. So 3 important things we have got. So let us use all those things now. So you remember initially we started the proof by considering what we have to prove exactly, and finally we reached to the conclusion that we have to simply prove that 3 line integrals is equal to 3 surface integrals, right? So our target is to prove the first line integral is equal to first surface integral. So let us start to work on the first surface integral now. So that surface integral, let me write here, that surface integral, consider double integration over S del cross f1i dot n cap ds, and value of this cross product we have already calculated, and in equation number 1 we have got its value. Let me write double integration over S. I need to check the equation number 1. So that value is, okay, let me write here, that value we have already got in equation 1, that is deba f1 by deba z j minus deba f1 by deba y k. So in equation number 1 we have already got its value, dot n cap ds, let me mention from 1. Okay, so let us take a dot product now. So I will take separate dot product, double integration over S. So it is deba f1 by deba z j cap dot n cap minus deba f1 by deba y k cap dot n cap ds. Okay, but see j cap dot n cap, we have got its value in equation number 3. So let us use this equation, this value which we have already got in equation 3 here. So this is equal to double integration over S. So its value deba f1 by deba z as it is, and its value is minus, so let me write minus here, deba f by deba y k cap dot n cap minus deba f1 by deba y k cap dot n cap ds. So I should mention here from equation number 3. Okay, so what can we take common? We can take k cap dot n cap common. We can take minus sign also common. So let me take it outside. So double integration over S, I am taking common here minus sign, deba f1 by deba z. See, this is capital F1 and this is small f. Small f, its value we have already seen. Small f, f of xy is equal to z. So we can replace this small f by z also, deba z by deba y. Minus sign we have already taken common, so plus will be there, deba f1 by deba y. And what we have taken common, k cap dot n cap ds. But see, we have already seen this k cap dot n cap ds, equation number 2. Yes, equation number 2 we have already seen. You can go back to this video and see. So in equation number 2 we have got its value is dx dy. Okay, so let me put it here, make a screenshot of it first, then I will go further. So let us continue. So this is equal to double integration over S minus deba f1 by deba z deba z by deba y plus deba f1 by deba y, and its value is dx dy. Let me mention from equation number 2. Okay, so we got 3 equations, equation 1, equation 2 and equation 3. So now we use all these 3 equations, right? Here we use equation 1, here 3 and here equation number 2. So now this type of term we have. So yes, but let me mention, but f1 is basically a function of 3 variables x, y, z. f1 is a function of 3 variables x, z and y. But again z is a function of 2 variables x and y. We have already seen, yes, z is equal to f of xy. You remember we have already seen this, z is equal to f of xy. It means z is again function of x and y. So we can write in this way. So this type of diagram we have, then we can go for a chain rule. So by chain rule, suppose we want to find the derivative of f1 with respect to y. Suppose we have to find derivative of f1 with respect to y. Then we have 2 ways to find its value. So either you can go via z or you can directly find the derivative. So if you go via z, then we will have deba f1 by deba z into deba z by deba y. Derivative of f1 with respect to z and derivative of z with respect to y. And the second option is you can directly find its derivative. So del bar f1 by del bar y. So by chain rule we will have this, but see, this is nothing but the value of this bracket. Okay, whatever we have got in this bracket, that is nothing but this one. So this entire term can be easily replaced by this del by f1 by del by y only. So let me write therefore double integration over s del cross f1I dot, let me write here, dot n cap ds is equal to double integration over s, minus sign is there, the value of this bracket is del bar f1 by del bar y and this dx dy. Okay, dx dy. So this is a very important thing we have got. So let me call it as equation number 4. Okay, so here we completely work on that right hand side, the surface integral. So let us work on left hand side also, that is line integral. So let me remove this part to write some more steps. Okay, so let us work on left hand side now. So consider that left hand side was integration over c f1 dx. So the same thing we can write in this way also, f1 dx plus 0 dy. Dy is not there, so we can write 0 into dy. So now we can apply Green's theorem here. So Green's theorem says this is surface double integration over s, getting? So derivative of 0 with respect to y, so its derivative will be 0, minus derivative of f1 with respect to x. So simply I am using Green's theorem, okay, and obviously we should write dx dy. See, derivative of this one with respect to x 0 and derivative of f1 with respect to y dx dy. So I should mention by Green's theorem. Okay, so let me write Green's theorem so you can easily understand. So this is p dx plus q dy. So this is equal to double integration over s del bar q by del bar x minus del bar p by del bar y dx dy. So this is our Green's theorem. So here p is f1 and q is 0. So that's why simply I use the Green's theorem and I got this one. Okay, so let me remove this. Okay, so let me write in a simple way, double integration over s minus del by f1 by del by y dx dy, equation number 5. So tell me, both of them are same? Yes, both of them are having equal value. So therefore from 4 and 5, so from 4 and 5, we can say the left hand side is equal to right hand side. So therefore integration over c f1 dx is equal to double integration over s. Okay, what we have calculated here, del cross f1I dot n cap ds. So this is, in this way we proved that line integral is equal to surface integral for only for first integral. Okay, so similarly we can write double integration over c f2 dy is equal to double integration over s del cross f2j dot n cap ds, and similarly we can write integration over c f3 dz is equal to double integration over s del cross f3k dot n cap ds. Okay, so in this way separately we proved all these three integrals are equal, so we can add them. Okay, make a screenshot of it, then I will go further. So if we add all these three integrals, then we will have, let me write, therefore integration over c f1 dx plus integration over c f2 dy plus integration over c f3 dz is equal to double integration over s del cross f1I dot n cap ds plus double integration over s del cross f2j dot n cap ds plus integration over s del cross f3k dot n cap ds. So therefore, okay, finally we can write, so therefore if you add, we will have, this is nothing but a bar dot dr bar, and if you add right hand side, this is nothing but double integration over s curl of a bar dot n cap ds. So at the beginning of this theorem we have already discussed how we got this one from this one. Okay, so finally we proved this Stokes theorem. So make a screenshot of it, then we will stop. Thank you. See you.